Look at yourself in the mirror. Go ahead. Really look. What you're seeing is one of the strangest creatures that ever evolved on this planet. Not because of your big brain or your ability to walk upright or your opposable thumbs. No, what makes you truly bizarre in the animal kingdom is something you probably never think about. You're naked, almost completely hairless, and that shouldn't be possible. There are over 200 species of primates alive today. Gorillas, chimpanzees, orangutans, baboons, lemurs, tarsiers, every single one of them is covered in fur. Thick protective fur that shields them from the sun, keeps them warm at night, protects their skin from scratches and insect bites. Then there's you, a few wispy hairs on your head, some patches in strategic locations, and otherwise just bare exposed skin stretched over your entire body. If you're using this video to fall asleep, perfect. That's exactly why I make these. So maybe hit subscribe, and here's what I want to know. Where are you right now and what time is it? Seriously, comment below. Are you in Tokyo at dawn, London at midnight, São Paulo during an afternoon rainstorm? I read every single one, and it's wild to think we're all scattered across this planet, descendants of the naked apes who somehow conquered the world. This isn't just a curiosity, it's one of the deepest mysteries in human evolution. Because losing your fur is, from an evolutionary standpoint, completely insane. Hair is one of the defining features of mammals. It's been around for over 200 million years. It's what separates us from reptiles and birds. Every mammal on Earth has fur, from tiny mice to massive whales. Yes, even whales have some hair. Except us. Well, us and a few other weird exceptions. Elephants, hippos, naked mole rats. And there's a pattern there. Those animals all have very specific reasons for being hairless. Elephants and hippos are massive and live in hot climates. They lost their fur because they overheat easily. Naked mole rats live underground where fur would just trap dirt and parasites. But humans, we're not particularly large. We don't live exclusively in hot climates. We somehow spread to every environment on Earth, from the Arctic to the tropics. So why did we lose our protective fur coat? Why would evolution strip away something that every other primate clearly needs? The answer, as you're about to discover, might be the reason we're here at all. The reason we built cities and invented language and eventually created everything from the wheel to the smartphone. Our nakedness might be the most important thing that ever happened to our species. Now, scientists have been arguing about this for over a century. And here's where it gets interesting. There's no consensus. None. We have half a dozen competing theories, and each one sounds completely plausible until you hear the next one. There's the Savannah Theory, which says we lost our hair because we started hunting in the hot African sun and needed to cool down through sweating. Makes sense, right? Except it doesn't explain why we kept the hair on our heads, the one place where you'd most want to lose it if overheating was the problem. Then there's the Aquatic Ape Hypothesis. This is the controversial one, the theory that gets scientists either really excited or really angry. It suggests that our ancestors spent a significant period of time living in and around water, wading through shallow lakes and rivers, eating seafood. And we lost our fur for the same reason dolphins and whales did, because fur is useless when you're wet all the time. Sounds crazy, except it explains a bunch of other weird things about human anatomy that the Savannah Theory doesn't. There's also the Parasite protection hypothesis. This one's delightfully gross. It argues that we lost our body hair to make it harder for parasites, ticks, lice, fleas to hide on our skin. With less hair, we could see the little bloodsuckers and pick them off before they made us sick. In a world where diseases killed more of our ancestors than predators or starvation, this would have been a massive survival advantage. And then there's sexual selection. The idea that we lost our hair because our ancestors thought naked skin was attractive. That smooth skin became a sign of health and youth, and over thousands of generations we literally bred ourselves hairless, because that's what everyone found sexy. Here's the thing, they might all be right. Evolution doesn't work in straight lines. It's messy, complicated, driven by multiple pressures all at once. Maybe we lost our hair for several different reasons, each one reinforcing the others until we ended up as the naked apes we are today. But the timing matters. This didn't happen recently. The genetic evidence suggests humans lost most of their body hair somewhere around 1 to 2 million years ago. That's deep time. That's before modern humans even existed. This happened to our ancestors, early members of the genus Homo, probably Homo erectus, who were just beginning to look and act sort of like us. 1 million years ago, the world was a profoundly different place, and the creatures who would become us were facing challenges we can barely imagine. Climate chaos, predators, starvation, disease, and somehow, in the middle of all that, they lost their fur and survived anyway. More than survived, they thrived. So let's go back. Way back. Let's trace the journey from our furry ancestors to the smooth-skinned humans who eventually took over the planet. Let's explore every theory, examine the evidence, and try to solve one of evolution's strangest mysteries. Why did humans become the naked ape? Let's go back. Way back. Before humans lost their hair, before we became the naked apes standing out like sore thumbs in the mammalian family tree, back to a time when our ancestors looked a lot more like what you'd expect from a primate, covered head to toe in thick, functional body, hair. 6 to 7 million years ago, somewhere in Africa, your distant ancestor was swinging through trees or walking along forest edges, and here's what we know for certain. They were hairy. Not just a little fuzzy, completely covered in fur, just like modern chimpanzees, just like gorillas, just like every other primate on the planet except us. This ancestor, the last common ancestor we shared with chimpanzees, would have looked nothing like a modern human. Think more chimpanzee than person. Body covered in dense black or dark brown hair. Longer on the head, shorter on the palms and soles, but covering virtually every square inch of skin. This wasn't fashion. This was essential survival equipment. Because here's the thing about body hair. It's one of the most successful evolutionary innovations in mammalian history. Hair keeps you warm when it's cold, protects your skin from the sun's ultraviolet radiation when it's hot. It provides sensory feedback, those individual hairs detecting air movement, insects, physical contact. It offers camouflage in forest environments. It even serves social functions, making you look bigger and more intimidating when raised during threat displays. Every mammal on Earth, except a handful of weird exceptions, has figured this out. Hair works. It's cheap to produce, easy to maintain, incredibly versatile. Natural selection has refined it over hundreds of millions of years into dozens of specialized forms. Dense underfur for insulation, guard hairs for water resistance, whiskers for navigation, manes for social display. Your ancestors had all of this. They had been perfecting their hair for longer than we can really comprehend. Hundreds of millions of years of mammalian evolution, all focused on developing and maintaining the perfect coat of fur for survival. So what happened? Why would evolution throw away one of its greatest hits? Let's start by understanding what we lost. Early hominins, the first human ancestors that split off from the chimpanzee line, almost certainly retained substantial body hair for millions of years after the split. We're talking about species like Australopithecus, The famous Lucy and her relatives who lived between 4 and 2 million years ago. These weren't humans. Not yet. They were something in between. Walking upright on 2 legs, which were revolutionary, but still spending significant time in trees. Still living in mixed woodland and savanna environments where being hairy made perfect sense. Lucy probably looked startling to modern eyes. An upright walker with human-like hands and feet, but covered in ape-like body hair. Her face would have been largely hairless like ours, a trait we seem to have retained from deep in our primate ancestry. But her arms, legs, back and torso, all covered in dense protective fur. This configuration had served primates well for tens of millions of years. The thermal regulation was perfect. During cool nights, the hair trapped a layer of warm air against the skin. During hot days, it actually provided insulation against heat, keeping the skin cooler than if it were exposed directly to the sun. Think about it. You go outside on a blazing hot day wearing a dark shirt. You feel like you're cooking, right? But that's because human clothing is usually a single layer. Natural fur works differently. It creates a dead air space between the environment and the skin. That space acts as insulation in both directions. Heat from outside has trouble getting through, and your body's metabolic heat has trouble getting out. This is why animals in the hottest parts of Africa, lions, zebras, giraffes, they all keep their fur. It's not despite the heat, it's because of it. The UV protection alone is worth the metabolic cost. Ultraviolet radiation doesn't just cause sunburn, it damages DNA, destroys vitamin folate in the blood, increases cancer risk. For a terrestrial mammal living under the African sun, having fur is like wearing SPF 1000 sunscreen that never wears off. But hair does more than regulate temperature and block UV. Each hair is a sensory organ. At the base of every hair follicle sits a complex of nerve endings that can detect the slightest movement. When a mosquito lands on a monkey's arm, the hair moves before the insect even touches skin. This gives the animal time to swat it away before it bites. This might seem trivial until you realize that insect-borne diseases are one of the biggest killers in African ecosystems. Malaria, sleeping sickness, dozens of parasitic infections, they all rely on insect vectors. Anything that helps you detect and remove insects before they bite is a major survival advantage. Then there's social signaling. Primate body hair isn't uniform, it's patterned, with different lengths and densities in different areas. These patterns serve as species recognition markers. They help individuals assess age, health, and genetic fitness. During threat displays, many primates can raise their hair, making themselves look larger and more intimidating. Humans lost all of this. Every single advantage that body hair provided, we threw it away. And evolution doesn't make changes like that casually. The developmental machinery for growing hair is expensive. Millions of years of refinement went into perfecting it. To lose it means that something else, some other selective pressure, had to be even more powerful than all the combined advantages hair provided. This is what makes human hairlessness so puzzling. We didn't just reduce our hair slightly, we eliminated it almost entirely. And we did it in a remarkably short time by evolutionary standards. The fossil evidence suggests that full hairlessness probably emerged somewhere between 1 and 2 million years ago. We can't see hair in fossils, obviously, but we can see other markers. The development of sweat glands, for instance. Humans have an insane number of eccrine sweat glands compared to other primates. These glands only make sense if you don't have fur. Sweating through a thick coat of hair is pointless. The water just gets trapped in the fur and sits there. You don't get evaporative cooling, which is the whole point of sweating. Genetic studies support this timeline. The genes controlling hair growth are remarkably conserved across mammals. The basic developmental pathway is ancient, shared by everything from mice to elephants. But humans have accumulated specific mutations in hair-related genes that reduce hair shaft thickness, decrease follicle density, and shorten the growth phase of hair development. These mutations are surprisingly recent in evolutionary terms. They show up in the human lineage but not in Neanderthals or Denisovans, at least not in the same configuration. This suggests that full modern human hairlessness might have emerged even more recently than we thought, possibly as late as 200,000 years ago, though the process probably began much earlier. But here's what's really wild. The genetic changes required for dramatic hair loss are minimal. You don't need to rework the entire developmental system. Just a few mutations in regulatory genes can dial hair production way down. One mutation might reduce follicle density. Another might shorten the growth phase. Another might thin the hair shaft diameter. Make 3 or 4 changes, and suddenly you've gone from ape to human in terms of body hair coverage. This tells us that hair loss could have happened relatively quickly once selective pressure favoured it. Within maybe 50,000 to 100,000 years, which is nothing in evolutionary time. A couple thousand generations of consistent selection, and your lineage goes from fully furred to nearly naked. But here's the critical question. What selective pressure could possibly be strong enough to overcome all the advantages of having hair? To understand this, we need to look at the handful of other mammals that lost their hair. And this list is revealing. Elephants, rhinoceroses, hippopotamuses, walruses, whales, dolphins. Notice anything? They're all massive. Really, really massive. The smallest hairless mammals are still huge by primate standards. Size matters here because of the relationship between volume and surface area. As an animal gets bigger, its volume increases faster than its surface area. This creates a heat management problem. Large bodies generate enormous amounts of metabolic heat, but have relatively less skin surface area through which to dissipate it. Hair makes this worse. It acts as insulation, trapping heat. For a massive animal living in a hot environment, this is deadly. So the evolutionary solution is to lose the fur, maximize skin exposure, and use other mechanisms like mud wallowing, water immersion, or massive ears, think elephants, to dump excess heat. But humans aren't massive. We're medium-sized primates. We don't have the heat management problems of elephants. So why did we lose our hair? There's one other category of hairless mammals. Aquatic species, whales, dolphins, manatees. They lost their hair because fur is useless underwater. It loses insulating properties when waterlogged and creates drag when swimming. These animals replaced fur with blubber for insulation and smooth skin for hydrodynamic efficiency. This is where things get interesting for human evolution, because humans are weird. We're not massive like elephants, but we're not aquatic like dolphins. We're something else, something that lost its hair for reasons that don't fit the usual mammalian patterns. Our ancestors made a trade-off. They gave up the protection, the insulation, the sensory advantages, and the social signaling functions of body hair. In exchange, they got something else, something so valuable that it was worth losing all those benefits. But what could possibly be worth that much? What advantage could be so powerful that it would drive evolution to strip away millions of years of refinement? The answer isn't simple. It's not just one thing. It's a combination of factors that came together in a unique way in the human lineage. Environmental pressures, behavioral changes, technological innovations, and quite possibly one of the most severe population bottlenecks in mammalian history. Because around the same time we are losing our hair, somewhere between 1 and 2 million years ago, something else was happening to our ancestors. They were changing how they lived, how they moved, how they hunted, how they dealt with the brutal African climate that was oscillating between extremes. The genetic evidence from that period shows population crashes. Long periods where human ancestors were reduced to tiny scattered groups. Times when every advantage mattered, when any adaptation that improved survival, even slightly, would be seized upon by natural selection and amplified across generations. Hair loss wasn't random. It wasn't an accident. It was a response to a specific set of challenges that our ancestors faced. Challenges that made being naked, as vulnerable as that sounds, actually the better option. And to understand those challenges, we need to look at where our ancestors were living and what they were doing. We need to examine the environment that shaped them, the behaviours they were developing, and the desperate circumstances that made losing their hair not just advantageous, but necessary for survival. So you've got these early humans wandering around Africa about 2 to 3 million years ago, and their world is changing in ways that will fundamentally alter everything about what it means to be human. The climate is shifting. Forests that had sheltered primates for millions of years are shrinking, fragmenting, giving way to something entirely different. Grasslands, vast open savannas stretching to the horizon. And your ancestors, these ape-like creatures who had spent their entire evolutionary history swinging through trees and foraging in dense woodland, suddenly found themselves exposed, vulnerable, standing upright in an environment with nowhere to hide. This is where one of the most compelling theories about human hairlessness begins. It's called the Savannah Theory, sometimes the thermoregulation hypothesis, and it goes something like this. When your ancestors moved out onto those open grasslands, they faced a problem that no other primate had ever encountered at that scale: heat. Not just any heat, but the brutal, relentless, inescapable heat of the African sun beating down on exposed skin for hours at a time. No tree canopy to shelter under, no dense forest to retreat into when midday temperatures soared. Just endless grass, scattered acacia trees, and that merciless sun. But here's where it gets interesting. Your ancestors didn't just need to survive the heat, they needed to exploit it. Because they had discovered something revolutionary, a hunting technique that would become one of the most effective strategies in human history. Persistence hunting, the ability to chase prey animals until they literally collapsed from heat exhaustion. Think about what that means. You're a human. Roughly 2 million years ago, you've spotted a kudu or an antelope, a large ungulate that can sprint at speeds you could never match. In a straight race, that animal leaves you in the dust every single time, but you figured something out, something that will change everything. That animal, fast as it is, has a fatal weakness. It can't cool down while running. Most mammals cool themselves primarily through panting. They have to stop, stand still, and breathe rapidly to dissipate heat. Humans developed something different. Something that would prove to be one of the most important adaptations in our entire evolutionary history. We became sweating champions. Not the apocrine sweat glands that most mammals have, concentrated in specific areas, producing that thick, odorous sweat. No, we developed eccrine sweat glands, millions of them, covering our entire bodies. These glands produce thin, watery sweat that evaporates quickly, creating a cooling effect that works even while we're moving. It's basically biological air conditioning, and it only works efficiently on bare skin. Here's why that matters. Take that kudu you're chasing. It sprints away fast and terrified. You jog after it at a pace you can maintain for hours. The kudu stops, exhausted, panting heavily to cool down. You keep coming. not running flat out, just maintaining that steady, relentless pace. The kudu sees you approaching and panics, sprinting away again. You follow. This happens again and again. Each time the animal gets more exhausted, more overheated. Each time you're just there, still coming, still moving. Your body temperature stays regulated because you're sweating continuously, and that sweat is evaporating off your bare skin, carrying away heat faster than you can generate it. The kudu doesn't have this advantage. Its fur traps heat. Its panting requires it to stop moving. After several hours, maybe 6 or 8 or 10, that kudu's body temperature reaches critical levels. Its muscles stop responding properly. It becomes disoriented. Eventually it collapses. You walk up to it with your simple stone tools and finish the job. This is how our ancestors hunted for hundreds of thousands of years. Not with speed, but with endurance. Not with strength, but with superior thermoregulation. And it absolutely required being mostly hairless. Because here's the physics of it. Fur is an excellent insulator. That's its entire evolutionary purpose. It traps a layer of still air next to the skin, preventing heat transfer. For most mammals, this is perfect. It keeps them warm when it's cold and provides some protection from the sun when it's hot. But when you're generating massive amounts of internal heat through sustained exercise, insulation becomes your enemy. You need to dump that heat as fast as possible, and fur prevents that. Even worse, if you're trying to cool down through evaporative sweating, fur completely undermines the process. Sweat gets trapped in the hair, saturates it, and just sits there instead of evaporating. You end up with a hot, wet, insulating layer that makes overheating even more likely. So the theory goes that as our ancestors specialized in persistence hunting on the African savanna, natural selection strongly favored individuals with less body hair. Each generation, these slightly less hairy individuals could hunt more effectively. They could maintain pursuit longer. They could bring down larger prey. They were more successful, better fed, more likely to survive and reproduce. Over hundreds of thousands of years, this selection pressure drove human body hair to near extinction. We didn't lose it everywhere. We kept it on our heads, where it actually helps by providing shade for the brain, protecting against both heat and sun damage. We kept our eyebrows, which channel sweat away from our eyes. We kept patches in areas that still serve specific functions. But the vast majority of our body hair simply became unnecessary, even counterproductive, and evolution trimmed it away. The evidence for this theory is actually pretty compelling. Start with modern hunter-gatherers. The San people of the Kalahari Desert in southern Africa still practice persistence hunting. Researchers have followed them on hunts that lasted 8 hours or more, covering distances of 20 to 35 kilometers in midday heat, exceeding 40 degrees Celsius. That's 104 degrees Fahrenheit. These hunters maintain a jogging pace for hours, tracking wounded or targeted animals until the prey collapses from hypothermia. The hunters themselves show core body temperature increases, but they remain within safe ranges because of their extraordinary sweating capacity and bare skin. Studies have measured sweat rates in these hunters exceeding 3 liters per hour. That's an insane amount of fluid loss, but it's what keeps them functional in conditions that would kill most mammals. Or look at the Tarahumara people of Mexico, famous for running down deer in the mountains of the Copper Canyon. These hunters can maintain running speeds for 48 hours or more, covering distances that would seem impossible to anyone who hasn't witnessed it. Again, superior thermoregulation through sweating on bare skin is the key adaptation that makes this possible. The correlation with bipedalism makes the theory even stronger. Humans are the only fully bipedal apes, and bipedalism itself offers significant advantages for long-distance travel in open environments. Walking or running upright exposes less body surface to direct sunlight compared to quadrupedal movement. During midday, when the sun is directly overhead, a bipedal human presents roughly 1/4 the surface area to solar radiation that a quadrupedal animal of similar size does. That's a massive reduction in heat absorption. Combine bipedalism with hairlessness and enhanced sweating, and you've got an animal that can operate in midday savanna heat that forces most predators to seek shade. The energy efficiency is remarkable. Studies of human locomotion show that bipedal walking and running are extraordinarily efficient compared to quadrupedal movement in most other mammals. At normal walking speeds, humans use less energy per distance travelled than any other animal except horses. This efficiency means we generate less waste heat for the same amount of movement, making thermoregulation easier. When you combine efficient bipedal locomotion with superior cooling capacity, you get an endurance predator unlike anything else in nature. Not the fastest, not the strongest, but capable of outlasting almost anything over sufficient distance and time. The fossil and archaeological evidence supports this timeline. Around 2 million years ago, multiple things happened simultaneously in the human fossil record. Brain sizes begin increasing significantly. Stone tool technology becomes more sophisticated. Evidence of meat consumption increases dramatically, and crucially, we see anatomical changes that suggest adaptations for long-distance running. Longer legs relative to body size, shorter toes, changes in hip and knee structure that improve running efficiency, the development of the nuchal ligament, a structure that helps stabilize the head during running and is absent in apes but present in humans and other running mammals. All of these changes cluster around the same period when climate data shows the expansion of grasslands across East Africa. The timing is too perfect to be coincidental. But here's where the Savannah Theory runs into problems. Because if hairlessness is such an advantage for savanna mammals that need to thermoregulate during sustained activity, why didn't it evolve in other species? Lions hunt in the heat. Wild dogs run down prey over long distances. Hyenas travel enormous ranges. Zebras and wildebeest migrate hundreds of kilometers. Yet all of these animals remain furry. Some of them, like lions, actually maintain pretty substantial coats despite living in hot environments. If hairlessness is the solution to savanna thermoregulation, why are humans the only mammals that evolved it? The critics of the Savannah Theory point to this apparent contradiction as evidence that something else must be going on. They argue that if heat stress and persistence hunting were sufficient evolutionary pressure to remove body hair, we should see hairless or nearly hairless versions of other savanna predators and prey. But we don't. Even the African wild dog, which practices cooperative pursuit hunting similar to human persistence hunting, maintains a full coat. So either the selective pressure wasn't as strong as the theory suggests, or there were other factors specific to humans that made hairlessness advantageous in ways that don't apply to other species. Maybe it wasn't just about thermoregulation. Maybe the combination of factors, bipedalism, tool use, social cooperation, changing diet, all created a unique ecological niche where hairlessness provided compound advantages that individually wouldn't have been sufficient. There's also the question of timing. The fossil evidence suggests humans were already substantially less hairy than other apes before the major expansion onto savannas. We can infer this from the evolution of dark skin pigmentation, which only becomes necessary when fur no longer provides protection from solar radiation. Genetic studies of melanin genes suggest dark skin evolved in the human lineage at least 1.2 million years ago, possibly earlier. This means significant hair loss probably happened before the period when persistence hunting became a dominant strategy. So maybe the savanna environment didn't cause hair loss. Maybe it just strongly reinforced and completed a process that had already begun for other reasons. Despite these valid criticisms, the thermoregulation hypothesis remains the most widely accepted explanation among anthropologists. The physics is undeniable. Bare skin plus eccrine sweating is dramatically more effective for cooling during sustained exercise than any alternative system. The ethnographic evidence from modern hunter-gatherers demonstrates that humans can and do exploit this advantage in ways no other mammal can match. The fossil record shows anatomical adaptations for endurance running, appearing at roughly the same time climate data indicates savanna expansion. And crucially, we know from genetic evidence that the changes in sweat gland distribution, the proliferation of eccrine glands across the entire body, happened during this same time period. So maybe the answer isn't that the Savannah theory is wrong, but that it's incomplete. Maybe hairlessness in humans resulted from multiple selective pressures, with thermoregulation being the strongest but not the only factor. The Savannah environment created conditions where being hairless was advantageous, but other aspects of human evolution, our social structures, our tool use, our particular ecological niche, meant that the trade-offs of hairlessness were more acceptable for us than they would be for other species. A lion might benefit from better cooling, but it would lose camouflage, protection from biting insects, and social signaling through mane development. The costs would outweigh the benefits. For humans, already committed to an ecological strategy based on endurance, cooperation, and tool use, the benefits of hairlessness exceeded the costs in ways that were unique to our lineage. What we're left with is a theory that's probably mostly right, but definitely not complete. Yes, the move onto the savanna and the adoption of persistence hunting created strong selection pressure for enhanced thermoregulation. Yes, losing body hair and developing extensive eccrine sweating was the solution that evolution found. But this happened in the context of many other changes, social, cultural, technological, that all influenced which traits were advantageous and which weren't. The savanna didn't just make us hairless, it made us human. And hairlessness was part of a much larger package of adaptations that turned a moderately successful ape into the most dominant predator the planet had ever seen. But here's another theory about why we lost our fur, and honestly, it might be the most compelling one yet. It's also kind of gross, so if you're squeamish about bugs, maybe take a deep breath. Ready? Here it is. We lost our body hair because it was crawling with parasites. Think about it. Your ancestors weren't living in houses with running water and soap. They weren't washing their clothes or taking showers. They were living in close quarters with other humans, sleeping on the ground, spending their days hunting and foraging through grasslands and forests. And their body hair, that thick coat of fur that covered most of their bodies, was the perfect habitat for every parasite imaginable. Lice, ticks, fleas, mites. All of them loved living in human body hair. It was warm, protected, with a constant food source literally flowing underneath. For a parasite, the hairy human body was paradise, and for humans it was a nightmare of itching, infection, and disease. Because here's the thing about parasites. They're not just annoying. They're vectors for some of the deadliest diseases in human history. Lice spread typhus. Ticks spread relapsing fever. Fleas spread plague, mites cause scabies, which leads to secondary infections that can kill. In a world without medicine, without antibiotics, without even basic hygiene, parasites were one of the most dangerous threats humans faced. Now, imagine you're living about 1 million years ago. Your people are starting to spend more time in social groups, not just families, but extended communities of maybe 20, 30, 40 individuals. You're sleeping close together for warmth and protection. You're sharing food, you're grooming each other, you're engaging in all the social behaviors that make human cooperation possible, but you're also creating the perfect conditions for parasite transmission. Every time you groom someone, you risk picking up their lice. Every time you sleep next to someone, their fleas can jump to you. Every close contact is an opportunity for parasites to spread from one host to another, and in a small group living in close quarters, one person's parasite problem quickly becomes everyone's parasite problem. The selective pressure this created was enormous. Individuals who had less body hair had fewer places for parasites to hide. They were easier to keep clean. They suffered fewer infections. Most importantly, they were more attractive as mates. Sexual selection again, but this time driven by health rather than just aesthetics. A hairless or nearly hairless individual was advertising their parasite-free status. They were signaling that they were healthy, that they had good genes, that they wouldn't infect you or your children with disease-carrying bugs. In a world where parasites could kill you or your offspring, choosing a hairless mate was a survival strategy. And we have genetic evidence that this actually happened. Scientists have studied the evolutionary history of human lice, and what they found is fascinating. There are 2 main types of lice that affect humans: head lice and body lice. They're closely related, clearly evolved from a common ancestor, but they're genetically distinct enough that we can date when they split apart. Body lice, the ones that live in clothing and bedding rather than directly on the body, diverge from head lice somewhere between 83,000 and 170,000 years ago. That's recent in evolutionary terms, very recent, and it tells us something profound. Humans lost most of their body hair long before they invented clothing. The body lice had to evolve a new survival strategy because their traditional habitat, thick body hair, was disappearing. Head lice, meanwhile, kept right on living in our head hair because we kept our head hair. They didn't need to evolve. Their habitat remained intact. The genetic split between head lice and body lice is essentially a molecular clock marking when humans became mostly hairless. But the evidence goes deeper than just lice genetics. Look at our closest relatives, the great apes, chimpanzees, gorillas, orangutans. They all have thick body hair, and they all have massive parasite loads. A typical wild chimpanzee might be hosting dozens of species of parasites at any given time. Lice, ticks, mites, intestinal worms, you name it. Their fur is essentially a mobile ecosystem of disease. Primatologists who study wild apes spend huge amounts of time documenting parasite infestations. They've observed chimpanzees spending hours every day grooming each other, picking through fur to remove parasites. It's not just social bonding, though, that's part of it. It's necessary hygiene. Without constant grooming, the parasite load becomes unbearable. Now imagine our ancestors faced with the same problem, but with an additional challenge. They were spending more time on the ground, in grasslands where ticks were abundant. They were living in larger social groups where parasites could spread more easily. They were developing increasingly complex social behaviors that required close physical contact. The parasite problem wasn't just annoying anymore, it was becoming a serious threat to survival. Natural selection responded in the most direct way possible: eliminate the habitat. Individuals born with genes for less body hair had fewer parasites. They spent less time dealing with itching and infection. They could devote more energy to finding food, having children, and contributing to their social group. Most crucially, they were healthier and therefore more attractive as mates. Over hundreds of thousands of years, genes for body hair reduction spread through the population. Not all at once, not uniformly, but gradually and relentlessly. The selective advantage was simply too strong to resist. Every generation, hairier individuals suffered slightly more from parasites. Every generation, hairless individuals had slightly better reproductive success. The math of evolution did the rest. But here's where the hypothesis gets really interesting. We didn't lose all our hair. We kept head hair, pubic hair, and underarm hair. Why? If parasites were such a problem, why not go completely bald? The answer involves a fascinating trade-off between parasite protection and sexual selection. Head hair serves multiple functions. It protects the scalp from sun exposure and heat loss. It cushions the head from impacts. Most importantly, it's a powerful sexual signal. Thick, healthy hair indicates good nutrition, youth, and genetic fitness. The benefits of keeping head hair outweighed the parasite costs, especially if the hair could be regularly groomed. Pubic hair and underarm hair appear during puberty, right when sexual signaling becomes important. These patches of hair retain scent, allowing pheromones to linger and spread. In a species that was evolving increasingly sophisticated social and sexual behaviors, these scent signals were valuable. The hair in these regions creates more surface area for scent dispersal, making individuals more noticeable to potential mates. Again, the benefits outweighed the costs. But the rest of the body? The torso, arms, and legs that had once been covered in thick fur. That hair served no crucial function that couldn't be replaced by other adaptations. Better temperature regulation through sweating, protection from scratches through tougher skin, group cooperation replacing individual physical resilience. One by one, the benefits of body hair were replaced by other adaptations. The parasite costs, meanwhile, remained constant, so the hair went. This created a cascade of secondary adaptations. As body hair disappeared, human skin became more durable. Modern human skin is tougher and more resistant to minor injuries than that of other primates. We had to develop this toughness because we no longer had fur protecting us from thorns, sharp grasses, and rough surfaces. We also became more dependent on behavioral adaptations for protection. Clothing, when it eventually appeared, served multiple functions. It protected hairless skin from environmental damage. It provided warmth in cold climates. But it also created a new habitat for body lice, which is why those lice evolved to live in clothing rather than on bodies. The genetic timing suggests clothing appeared hundreds of thousands of years after hair loss began, which means our ancestors spent a very long time as mostly naked, hairless primates, managing just fine without either fur or clothing. They must have used other strategies, sitting on animal skins or grass padding to protect their bare skin, choosing campsites carefully to avoid thorny vegetation, using fire not just for cooking but for warmth during cold nights. These behavioral adaptations replaced the protection that fur once provided, but they also required intelligence, planning, and cooperation. Once again, we see how one evolutionary change, losing body hair, drove the selection for other traits, like increased cognitive ability and social coordination. The parasite hypothesis also explains some puzzling features of human behavior. We're obsessed with cleanliness in ways other primates aren't. Even in cultures without formal hygiene practices, humans spend significant time cleaning their bodies and their living spaces. We're instinctively disgusted by signs of parasitic infestation, recoiling from lice, ticks, and other bugs in ways that seem disproportionate to the actual threat. This isn't just cultural conditioning, it's evolved psychology. Our ancestors who were most disgusted by parasites, who worked hardest to avoid them, were the ones who survived to reproduce. We're also incredibly selective about physical contact. Unlike chimpanzees who will groom anyone in their social group, humans are much more discriminating. We reserve intimate physical contact for family members and close friends. We maintain personal space with strangers. Part of this is cultural, but part is likely evolved caution about parasite transmission. In a world where close contact could mean infection, being choosy about who you touched was a survival skill. Modern evidence continues to support the parasite hypothesis. In populations where humans retain more body hair, either through genetic variation or choice, parasitic infestations remain more common. Studies of body hair grooming in various cultures show consistent patterns. More hair means more time spent on parasite management. The correlation is clear and consistent across populations. There's even experimental evidence. Studies comparing parasite loads on shaved versus unshaved body parts show dramatically lower parasite numbers on hairless skin. The effect is so strong that many modern medical protocols call for shaving surgical sites before operations, specifically to reduce infection risk. Our distant ancestors discovered this advantage through natural selection. We've simply formalized it into medical practice. But like all evolutionary hypotheses, the parasite protection theory doesn't work in isolation. It complements the other theories rather than replacing them. Parasite protection created selective pressure for hair loss, but sexual selection amplified that pressure. Thermoregulation made hairlessness more practical in certain environments. Social signaling gave hairless skin additional advantages. All these factors worked together, creating multiple reinforcing pressures that drove the same evolutionary change. The timeline also matters. The genetic evidence suggests body hair loss began at least 1.2 million years ago, possibly earlier. This puts it right around the same time as the population bottleneck we discussed earlier. Remember those 1,280 breeding individuals struggling to survive in a world of climate chaos? They were also dealing with increased parasite pressure from living in close quarters, from reduced mobility forcing them to stay in contaminated areas longer, from weakened immune systems caused by poor nutrition. The bottleneck created exactly the conditions where parasite pressure would be most intense, and where any advantage in parasite resistance would be most valuable. Individuals who carried genes for reduced body hair entered the bottleneck with a slight advantage. They emerge from it with those genes fixed in the population. The survivors weren't just the ones who could find food and avoid predators. They were also the ones whose bodies were most resistant to the diseases that parasites carried. Hair loss was part of the survival package that got our ancestors through the worst crisis in human history. And once the population began expanding again after the bottleneck, the hairless traits spread with them. Every new population carried the genes for reduced body hair. Every migration took those genes to new environments. By the time modern humans, Neanderthals and Denisovans split into separate species, they all shared the trait of greatly reduced body hair compared to earlier hominins. The bottleneck had made hairlessness universal among all human lineages. This gives us a more complete picture of why we're naked apes, not because of one single factor, but because multiple pressures all pointed in the same direction. Parasites created the initial push. Sexual selection amplified it. Improved thermoregulation made it practical. Social living made it advantageous. And the population bottleneck locked it in place, ensuring that every human who came after would inherit this strange, nearly hairless body plan. We lost Our fur because evolution doesn't care about single causes. It cares about survival and reproduction, and for our ancestors, being hairless improved both. But before we settle too comfortably into the Savannah hypothesis, we need to talk about one of the most controversial, most debated, and most publicly fascinating theories in all of human evolution, the Aquatic Ape Theory. And here's the thing. This theory has been rejected by mainstream science for decades, dismissed as fringe speculation, yet it refuses to die. It keeps popping up in popular science books, documentaries, internet discussions. There's something about it that captures people's imagination in ways that dry academic papers about thermoregulation never quite manage. So let's dive in, literally. The aquatic ape theory was first proposed in 1960 by British marine biologist Alistair Hardy. He was a serious scientist, not some fringe crank. He'd spent decades studying ocean life, and one day he asked himself a simple question. Why are humans so different from other apes? And not just different, weird. Really profoundly weird in ways that savanna adaptations don't quite explain. Hardy looked at human bodies and saw features that reminded him of marine mammals. So he proposed something radical. What if our ancestors didn't just live on the savanna? What if they spent significant time in and around water? Maybe millions of years ago, some population of early humans found themselves living in coastal environments, wading into shallow waters, diving for shellfish, spending hours each day partially submerged. The theory languished in obscurity for over a decade. Then in 1972, Welsh writer Elaine Morgan picked it up and ran with it. She wrote a series of popular books starting with The Descent of Woman that laid out the aquatic ape hypothesis in compelling detail. Morgan wasn't a scientist. She was a television writer, but she was smart, persuasive, and she assembled what looked like a devastating list of evidence that mainstream anthropology was ignoring. Let's walk through her arguments, because they're genuinely fascinating, even if they're probably wrong. First, the obvious one, hairlessness. Marine mammals lose their fur. Seals, whales, dolphins, manatees, they're all essentially hairless. They've traded fur for subcutaneous fat, a thick layer of blubber under the skin that provides insulation in water far more effectively than hair ever could. Now look at humans. We're the only primates who lost our body hair. We're also the only primates with significant subcutaneous fat. Even lean humans have a layer of fat under their skin that other apes simply don't possess. Babies especially are remarkably chubby compared to other primate infants. Put an infant chimpanzee next to a human baby, and the difference is striking. The human baby looks like it's been preparing for a swim meet. Morgan argued this wasn't coincidence. This was adaptation to an aquatic lifestyle. We lost our hair, and gained fat because our ancestors spent enough time in water that natural selection favoured the same solutions that worked for seals and dolphins. Second, breath control. This one's subtle but genuinely interesting. Humans have extraordinary voluntary control over their breathing. We can hold our breath for minutes at a time with training. We can control our breathing consciously in ways that no other land mammal can match. This ability is so automatic we don't even think about it. But it's remarkable. Chimpanzees can't do it. Gorillas can't do it. Land mammals in general breathe automatically. Their respiratory systems are controlled by involuntary reflexes that they can't override. But aquatic mammals are different. Dolphins, whales, seals, they all have voluntary breath control because they need it. You can't have automatic breathing when you're diving underwater. You'll drown. So aquatic mammals evolved conscious control over their respiratory systems, and so did we. Morgan argued this only makes sense if our ancestors were regularly submerging themselves, diving for food, spending enough time underwater that automatic breathing became a liability rather than an asset. Third, the diving reflex. When you submerge your face in cold water, something fascinating happens. Your heart rate immediately drops. Blood flow redirects from your extremities to your core. Your body automatically prepares for an extended period underwater. This is called the mammalian diving reflex, and all mammals have it to some degree. But humans have an unusually strong version. Our diving reflex is more pronounced than any land mammal and comparable to semi-aquatic species like otters. Newborn babies have an especially powerful diving reflex. Put an infant underwater, and it will automatically hold its breath and begin swimming motions. This reflex fades as children age, but it's there at birth, suggesting deep evolutionary roots. Why would land-dwelling apes need such sophisticated aquatic adaptations? Fourth, our relationship with water. Humans are the only primates who actively seek out water for pleasure. Chimpanzees avoid deep water. They can't swim. Most apes will only enter water reluctantly and stay in the shallows. But humans? We love water. We swim recreationally. We build homes near water. Throughout history, human settlements have clustered around coastlines, rivers, and lakes. Yes, we need water to drink, but it's more than that. We're drawn to water in ways that seem to go beyond simple resource requirements. Morgan argued this affinity suggests an evolutionary history that included aquatic environments as a central component of human life, not just a resource to exploit. Fifth, the archaeological evidence. When you look at early human fossil sites, they're overwhelmingly near water. River valleys, lake shores, coastal areas. Now, conventional anthropologists explain this by pointing out that water attracts animals, and humans were hunting those animals. Plus everyone needs drinking water. But Morgan argued the association was too consistent, too strong. She pointed to evidence of shellfish consumption going back millions of years. Shell middens, the garbage dumps of ancient seafood meals, appear in archaeological sites far earlier than most people realize. Some researchers have found evidence of systematic shellfish harvesting by early humans dating back 2 million years. That's not occasional opportunistic snacking. That's a major dietary component. If our ancestors were regularly wading into shallow waters to collect shellfish, spending hours each day in water, that's exactly the kind of selective pressure that could drive the evolution of hairlessness, subcutaneous fat, and breath control. Sixth, the nose. Human noses point downward. Every other primate has nostrils that point forward or slightly upward, but human nostrils point toward the ground. This seems trivial until you think about what happens when you submerge yourself in water. Forward-pointing nostrils fill with water immediately. Downward-pointing nostrils don't. Morgan argued this simple anatomical feature makes perfect sense for a species that spent significant time with its head partially submerged, but makes no particular sense for a savanna runner. So there you have it. A collection of features that seem genuinely aquatic, that appear to have no clear explanation in the standard Savannah hypothesis, that together paint a picture of human ancestors who weren't just visiting the water's edge, but were intimately adapted to semi-aquatic lifestyles. It's compelling. It's elegant. It explains things that other theories struggle with, and mainstream science thinks it's almost certainly wrong. Here's why. The aquatic ape theory sounds great until you start looking at what's missing. If humans spent millions of years adapting to aquatic environments, there should be a whole suite of aquatic adaptations, not just a handful. Where are the webbed fingers and toes? Where are the ear and nose modifications that prevent water intrusion? Where are the changes to bone density that help with diving? Where are the eye adaptations for underwater vision? Marine mammals show dozens of coordinated adaptations for aquatic life. Humans show a few features that might be aquatic adaptations or might be something else entirely. More importantly, the fossil record doesn't support it. We have thousands of early human fossils in associated archaeological sites. They're near water, yes, but they're savanna environments, woodland edges, grasslands near rivers. There's no evidence of extended occupation in coastal environments until very late in human evolution. The anatomical changes associated with hairlessness appeared around 1 to 2 million years ago, but evidence of systematic coastal exploitation doesn't appear until maybe 200,000 years ago. That's a massive temporal gap. The adaptations supposedly caused by aquatic lifestyles appeared hundreds of thousands of years before humans were actually living aquatic lifestyles. And those adaptations that seem so convincingly aquatic? They all have perfectly good terrestrial explanations. Subcutaneous fat isn't just for aquatic insulation. It's also an efficient way to store energy in environments where food availability is unpredictable. It provides cushioning that protects against injury during long-distance travel. It serves as an energy reserve during pregnancy and lactation, which are metabolically expensive. Breath control isn't uniquely aquatic. It's also necessary for sustained speech. Humans are the only primates with complex language, and complex language requires the ability to control breathing consciously, to pause and time your breaths between utterances. The diving reflex exists in all mammals, and humans having a slightly stronger version doesn't require an aquatic evolutionary history. It might just be a byproduct of other respiratory adaptations. The downward pointing nose? That's also advantageous for preventing dust and debris from entering during running and digging, both common activities for savanna-dwelling humans. As for our love of water, that's probably cultural, not genetic. Humans also love fire, build homes near it, seek it out for pleasure, but nobody's proposing we evolved in volcanic environments. The shellfish evidence is real, but it doesn't require deep water diving. Most of those shells are from shallow water species you can collect by wading in knee-deep water at low tide. That's coastal resource exploitation, not aquatic adaptation. So why does this theory persist? Why do people keep bringing it up despite mainstream scientific rejection? Partly because Elaine Morgan was a brilliant writer who made the theory accessible and compelling to general audiences. Partly because it challenges scientific orthodoxy in ways that feel satisfying, the outsider questioning the establishment. But mostly because the aquatic ape theory, wrong as it probably is, got something genuinely important right. It recognized that humans are weird, that we don't fit neatly into standard models of primate evolution, that we have a collection of unique features that demand explanation, not dismissal. The mainstream Savannah hypothesis, for all its scientific acceptance, sometimes hand-waves away human uniqueness. Oh, we lost our hair for cooling. Oh, we developed subcutaneous fat for energy storage. Each feature gets explained individually, without asking whether the overall package makes sense. The aquatic ape theory, by contrast, tried to find a unified explanation, a single environmental pressure that could account for multiple features simultaneously. It failed, probably, but it failed in an interesting way. It asked the right questions even if it provided the wrong answers. And here's the thing about scientific theories. Being wrong doesn't mean being worthless. The aquatic ape hypothesis pushed researchers to look more carefully at human evolution to gather better evidence, to develop more sophisticated explanations for human uniqueness. Some researchers now think our ancestors might have spent more time in and around water than traditional models suggested. Not enough to drive major anatomical changes, but enough to influence behavior and culture. Coastal and riverine environments would have provided reliable food sources, refuge from predators, and access to resources unavailable on the open savanna. This isn't the aquatic ape theory, it's something more nuanced. Humans as opportunistic exploiters of aquatic resources, not aquatic specialists. But it acknowledges that water played a larger role in human evolution than we once thought. And we wouldn't be having that conversation without Elaine Morgan's controversial, probably wrong, but genuinely thought-provoking hypothesis. Sometimes the theories that turn out to be incorrect are the ones that move science forward by forcing us to question our assumptions and look at evidence we'd been ignoring. So the aquatic ape theory joins a long list of beautiful ideas killed by ugly facts. But its ghost still haunts human evolutionary studies, reminding us that our ancestors' path from the trees to the savanna might have included some detours we haven't fully appreciated yet. But here's where the story gets really interesting. Because losing body hair wasn't just about staying cool or avoiding parasites or adapting to water. It was also about sex. And before you roll your eyes, hear me out. Because Charles Darwin, the guy who figured out natural selection, also figured out something else. Sexual selection. The idea that traits don't just evolve because they help you survive. They evolve because they help you get chosen as a mate. And when it comes to human hairlessness, sexual selection might be the most important piece of the puzzle we've been missing. Think about it. You're standing in front of another human, maybe someone you're attracted to, maybe someone you need to negotiate with, maybe someone whose intentions you need to judge quickly because your life might depend on it. Now imagine that person covered head to toe in thick fur. Good luck reading their emotional state. Good luck figuring out if they're interested, angry, afraid, or lying. The fur hides everything. But take away that fur, expose the skin, and suddenly you have a canvas. A living, changing billboard that broadcasts emotional information with incredible precision. This is what bare skin gave us. The ability to communicate visually in ways that no other primate could match. When you're embarrassed, you blush. Blood rushes to the surface of your face, creating a visible signal that everyone around you can read instantly. When you're angry, your face flushes red. When you're frightened or shocked, you go pale. Blood drains away from your skin surface, creating a ghostly pallor that tells everyone something's wrong. These aren't conscious choices. You can't fake a true blush or suppress the pallor of genuine fear. These are honest signals, involuntary broadcasts of your internal emotional state, and they only work because your skin is bare. For our ancestors living in increasingly complex social groups, this was revolutionary. Pre-human primates had fur. They relied primarily on vocalizations, body postures, and facial expressions to communicate. These signals worked, but they had limitations. A howler monkey can't blush. A chimpanzee can't go pale with fear in a way that's visible through thick body hair. But a hairless human can broadcast emotional information across a crowded room without making a sound. You can see who's nervous, who's confident, who's attracted to whom, all just by reading skin tone changes. This created what biologists call an honor signaling system. In evolutionary theory, honor signals are communications that can't easily be faked because they're too costly or physiologically constrained. A peacock's tail is an honest signal of genetic fitness because only healthy males can afford to grow and maintain such an extravagant display. Human blushing is an honest signal because you literally cannot control it. When blood rushes to your face, everyone knows you're experiencing shame, embarrassment, or attraction, whether you want them to know or not. Now, Why would evolution favour this kind of involuntary honesty? Seems like a disadvantage, right? Being unable to hide your emotions sounds like a recipe for getting exploited. But here's the thing, our ancestors weren't living alone. They were living in groups, small, tight-knit communities where cooperation was essential for survival. In that environment, individuals who could be trusted were more valuable than individuals who could deceive. If your group is hunting together, raising children communally, and depending on each other to survive, you need to know who's reliable. You need to identify cheaters, free riders, people who'll take resources without contributing. Blushing and other involuntary skin responses made deception harder. They created a species that wore its emotions on its skin, literally. And in a social world where trust and cooperation meant the difference between survival and extinction, that transparency became a survival advantage. But sexual selection takes this even further. Because bare skin didn't just help with general social communication, it fundamentally changed how humans chose mates. Look at other primates. Baboons have enormous coloured patches on their hindquarters that signal sexual receptivity. Chimpanzees have dramatic genital swellings. These are honest signals of fertility, but they're pretty crude. They broadcast one piece of information. I'm fertile now. Human bare skin allowed for something far more sophisticated. Subtle, continuous communication of health status, emotional state, and genetic quality. Healthy skin has a particular glow, a luminescence that comes from good circulation and proper nutrition. Sick individuals look different. Their skin takes on a greyish or yellowish tone. Parasites, infections, and nutritional deficiencies all show up as visible changes in skin quality. Before modern medicine, these were critical pieces of information for mate selection. Choosing a healthy partner meant choosing someone who could survive long enough to help raise children, someone whose genes wouldn't burden offspring with disease susceptibility. The skin became a health monitor that everyone could read, and this created strong sexual selection pressures favouring hairlessness. Individuals with less body hair were easier to assess. You could see their skin quality, read their emotional state, judge their health and vitality at a glance. If you were choosing between two potential mates, one furry and harder to read, one bare and broadcasting clear health signals, who would you choose? Over thousands of generations, this preference would drive the evolution of increasing hairlessness, not because bare skin helped you survive in any physical sense, but because it helped you get chosen by desirable mates. And being chosen by healthy, attractive partners is its own kind of survival advantage. Your children inherit those desirable traits, making them more likely to be chosen in turn. This brings us to neoteny, which is one of the strangest and most fascinating aspects of human evolution. Neoteny means retaining juvenile characteristics into adulthood, and humans are incredibly neotenous compared to other primates. Baby chimpanzees have relatively flat faces, small jaws, and sparse body hair. As they mature, their faces become more prognathous, jutting forward. Their jaws enlarge, their body hair thickens dramatically. Adult humans, by contrast, maintain many juvenile traits throughout life. We have flat faces, small jaws, and relatively hairless bodies even in old age. We look in many ways like juvenile primates that never fully matured. This isn't an accident. It's the result of sexual selection favouring individuals who retained youthful appearance. Across cultures and throughout history, humans have consistently preferred mates who display neotenous features: larger eyes relative to face size, smoother skin, less facial and body hair, especially in females. These preferences have been documented in virtually every human society researchers have studied. They're not culturally arbitrary. They're deeply rooted in our evolutionary psychology. Why? Because neotenous features are honest signals of youth, and youth correlates with fertility and reproductive potential. A 20-year-old has more potential reproductive years ahead than a 40-year-old. That's just biology. So, evolution shaped human mate preferences to favor indicators of youth, and one of the strongest indicators is smooth, relatively hairless skin. This created a feedback loop. Sexual selection favored individuals with less body hair because they looked younger and were therefore more attractive. The most attractive individuals had more reproductive success. Their genes, including genes for reduced body hair, spread through the population. Over thousands of generations, humans became progressively more hairless, not through natural selection for survival, but through sexual selection for attractiveness. But here's where it gets really interesting. This process didn't affect everyone equally. Human populations show dramatic variations in body hair retention across different regions and ethnic groups. Northern European populations tend to retain more body hair than East Asian populations. Mediterranean populations fall somewhere in between. Indigenous American populations often have very sparse body hair. These variations reflect different evolutionary histories and different sexual selection pressures in different environments. In colder climates, some body hair retention might have provided thermal benefits, reducing the selective pressure for complete hairlessness. In tropical environments, being as bare as possible maximized cooling efficiency, intensifying selection for hairlessness. But sexual selection pressure varied too. In populations where other traits became more important for mate selection, maybe height, strength, or specific facial features, the pressure for hairlessness might have relaxed slightly, allowing some populations to retain more body hair. The result is the spectrum of human hair patterns we see today. All humans are relatively hairless compared to other primates, but we're not all equally hairless. And these variations tell the story of thousands of generations of different populations adapting to different environments while also responding to different cultural and sexual preferences. Gender differences in hair retention patterns tell us even more about sexual selection. Human males retain significantly more body hair than females on average. Facial hair, chest hair, back hair, all far more common and dense in males. This sexual dimorphism, meaning difference between sexes, is a classic signature of sexual selection. When one sex develops traits that the other doesn't, it usually means those traits are being selected for through mate choice or male-male competition. Male body hair likely served as a signal of sexual maturity and hormonal status. Testosterone drives both muscle development and body hair growth. A male with thick beard and body hair was broadcasting, "I have high testosterone, I'm sexually mature, I'm capable of competing with other males." For most of human evolution, these were desirable traits, not universally, not in every culture, but common enough that the genes for male hairiness remained in the population even as overall human hairlessness increased. Female body hair patterns tell a different story. Women retain head hair that grows longer than male head hair on average. They retain pubic and underarm hair, but significantly less. Body hair overall, especially on the chest, back and face. This pattern reflects sexual selection favoring more neotenous appearance in females. Across cultures, female beauty standards have consistently emphasized smooth, relatively hairless skin. This isn't cultural conditioning, at least not entirely. It's a deeply rooted preference that probably emerged hundreds of thousands of years ago. when hairlessness became associated with youth, health, and fertility. The evolutionary logic is straightforward. Males who preferred females with neotenous traits, including smooth skin, were choosing mates with longer potential reproductive windows. Those males had more offspring on average. Genes for preferring hairlessness in female mates spread. Simultaneously, females with naturally sparser body hair were chosen more frequently. Their genes spread too. Over thousands of generations, this created the sexual dimorphism we see today. But bare skin didn't just change how humans looked. It changed what they could do with their appearance. Because once you have bare skin, you have a canvas for decoration. And humans, uniquely among all species, became artists of their own bodies. Tattooing, body painting, scarification, these practices show up in virtually every human culture we've ever studied. The oldest evidence of body decoration goes back at least 40,000 years, probably much older. Archaeological sites contain ochre pigments clearly used for body painting, ancient tools designed for tattooing, skeletal remains showing deliberate scarification patterns. This wasn't random. This was systematic use of bare skin as a medium for cultural expression and social signaling. Try tattooing a gorilla. The fur hides everything. Try painting intricate designs on a chimpanzee's body. You're wasting your time. But human bare skin is perfect for permanent and semi-permanent decoration. Why did our ancestors start decorating their bodies? Sexual selection provides a compelling answer. Body decoration allowed individuals to signal group membership, social status, personal achievements, and aesthetic sensibility. These are all traits that would influence mate selection. A young man with elaborate tattoos might be signaling, "I was brave enough to endure pain. I'm part of a prestigious warrior society. I have the resources and connections to access rare pigments." A young woman with carefully applied body paint might be broadcasting, "I have the time and resources to maintain this appearance. I understand cultural aesthetics. I'm healthy enough to afford spending energy on decoration rather than just survival." These signals matter in mate selection. They communicate information about social value, cultural integration, and resource access. And they only work because human skin is bare enough to serve as a visible canvas. Different cultures developed different decorative traditions, but the underlying logic remained consistent. Use your visible skin to communicate information that might influence how others, especially potential mates, perceive you. In some cultures, this meant elaborate scarification patterns that signaled tribal affiliation and passage through initiation rites. In others, it meant temporary body painting that changed based on social context, elaborate designs for ceremonies and festivals, simpler patterns for everyday life. The Maori of New Zealand developed facial tattooing so sophisticated that each individual's moko was unique, a visual signature as distinctive as a fingerprint. Pacific Island cultures created full-body tattoo traditions that took years to complete, turning the human body into a walking work of art. African cultures developed scarification techniques that created raised patterns, visible even on the darkest skin, ensuring decorative signals remained readable regardless of pigmentation. All of this was possible because humans lost their body hair. The bare skin that initially might have evolved for thermoregulation or parasite protection became a medium for cultural innovation and sexual signaling. And this feedback loop, more bare skin leading to more sophisticated body decoration, leading to stronger sexual selection for bare skin, probably accelerated the loss of body hair in human populations. Because once body decoration became culturally important, Individuals with thicker body hair would be at a disadvantage. Their natural hair would interfere with tattoos, obscure body paint, and reduce the visibility of scarification. Sexual selection would favor individuals whose bodies provided better canvases. Over time, this would drive populations toward even greater hairlessness. The visibility of skin color itself became a factor in human evolution and social organization. In populations that lived in equatorial regions with intense sun exposure for thousands of generations, darker skin pigmentation evolved as protection against UV radiation. In populations that migrated to higher latitudes with less intense sunlight, lighter pigmentation evolved to allow adequate vitamin D synthesis. These adaptations had survival value, but they also created visible markers of geographic origin and ancestry. Humans are intensely visual primates. We're good at detecting small differences in appearance. Skin color variations would have been immediately obvious when different populations encountered each other. And like all visible traits, skin color became entangled with sexual selection and social preferences. Different cultures developed different aesthetic preferences, but the underlying mechanism remained the same. Bare skin made these variations visible. Visibility made them socially significant. Social significance created selection pressures that fed back into the evolutionary process. This doesn't mean skin color differences are biologically meaningful in any deep sense. They're not. Human genetic diversity in traits that actually matter, immune system function, cognitive ability, behavioral traits, those variations don't correlate with skin color, but the visibility of skin color variations made possible by hairlessness has shaped human social history in profound and often tragic ways. What we're left with is a picture of human hairlessness as partly a product of sexual selection and social signaling. Our ancestors didn't just lose their hair to stay cool or avoid parasites. They lost it because bare skin became a medium for communication, a canvas for decoration, and an honest signal of health and quality. Over hundreds of thousands of years, these factors created a species that was not only remarkably hairless compared to its relatives, but also uniquely capable of using that hairlessness for cultural and social purposes. We became the apes that painted themselves, that read emotions on each other's faces, that chose mates based partly on the glow of healthy skin. And all of this started with a simple change: the loss of body hair that made everything else possible. So we've explored all these fascinating theories about why humans lost their body hair, but here's the question that should be keeping you up at night. How do we actually know any of this happened? You can't exactly dig up a fossilized skin cell and check how hairy it was. Hair doesn't preserve like bones do. It decomposes, it vanishes, leaving almost no trace in the archaeological record. Yet somehow, scientists can confidently tell us that our ancestors lost their body hair somewhere between 1 and 2 million years ago. How? The answer lies in some of the most ingenious detective work in modern science, a combination of genetics, parasitology, and good old-fashioned archaeological inference that pieces together a story written in our DNA. Let's start with the most unexpected witness in this investigation. Lice. Yeah, those parasitic insects that probably made elementary school a nightmare for you. Turns out they're evolutionary historians. Because here's the thing about human lice. We have 3 distinct types. Head lice, that live in scalp hair, pubic lice that live in, pubic hair, and body lice that live in clothing and bedding. Each type evolved to specialize in its particular environment, and by studying their DNA, we can actually date when these evolutionary splits occurred. It's like having a genetic clock that ticks backward through time. Researchers analysed the mitochondrial DNA of all 3 lice species and compared them to chimpanzee lice, looking for the moment when their evolutionary paths diverged. What they found was remarkable. The split between human head lice and pubic lice happened around 3.3 million years ago, right around the time when early hominins were becoming bipedal and losing some body hair. But the really interesting date comes from body lice. These parasites didn't exist until humans started wearing clothes because they can't survive on bare skin. They need fabric to cling to. By dating the evolution of body lice, scientists could estimate when humans first started wearing clothing regularly. The answer? Somewhere between 70,000 and 170,000 years ago. Think about what this tells us. If body lice only evolved when we started wearing clothes, and they evolved relatively recently in evolutionary terms, that means we were already mostly hairless long before we invented clothing. We weren't wearing animal skins because we lost our hair. We lost our hair first, probably 1 million or more years ago, and only much later figured out we needed artificial protection. This is molecular clock dating at its finest, using the evolution of parasites to reconstruct the evolution of their hosts. But lice are just the beginning. The real evidence is written in our genome, in the specific genes that control hair growth. Scientists have identified several key genes that play crucial roles in determining how much body hair we grow, and by studying these genes we can understand how and when humans became the naked ape. The most important of these is a gene called HR, which stands for hairless. Despite the somewhat on-the-nose name, this gene is absolutely critical for hair follicle development. In mice, if you knock out the HR gene, they go completely bald. In humans, mutations in HR cause a rare condition called a trichia with papular lesions, where people lose all their body hair shortly after birth. Now here's where it gets interesting. When scientists compared the HR gene across different primate species, they found that humans have a unique variant. Not a complete knockout like in those rare genetic conditions, but a subtle modification that reduces body hair density without eliminating hair growth entirely. This variant appears to be universal in modern human populations, which tells us it became fixed in our genome, meaning it spread to every human alive, sometime deep in our evolutionary past. The selective pressure to maintain this variant must have been strong and sustained for it to spread so completely. Then there's FGF-bensive, fibroblast growth factor 5, a gene that controls hair length. This gene essentially tells your hair follicles when to stop growing. Mutations in FGF5 cause unusually long hair in various mammals. In humans, our version of FGF5 has been modified in ways that are consistent with reduced body hair. The gene works normally for scalp hair, allowing it to grow long, but appears to have different expression patterns for body hair, limiting its growth. This suggests that human hair loss wasn't a simple on-off switch, but a sophisticated reprogramming of where and how much hair grows. Another critical player is EDA, ectodisplicin A receptor, a gene that's involved in the development of skin appendages including hair, teeth, and sweat glands. Certain variants of EDR are associated with thicker, straighter hair and increased sweat gland density. Interestingly, different EDR variants show up in different human populations, with particularly distinctive versions in East Asian populations. This tells us that hair and sweating characteristics continue to be shaped by natural selection, even after the major hair loss event, with different environments favoring different configurations of these traits. What makes this genetic evidence so powerful is that we can use it to estimate when these changes occurred. By comparing human versions of these genes, with those of our closest relatives chimpanzees and bonobos, and calculating the rate of genetic mutation, scientists can work backward to estimate when the human-specific variants arose. The dates aren't perfect because mutation rates can vary, but they consistently point to a window between 1 and 2 million years ago, right around the time when our ancestors were evolving into Homo erectus, developing larger brains, more advanced tools, and probably more sophisticated thermoregulation. But genes alone don't tell the whole story. We need archaeological evidence to support the genetic timeline, and here's where things get tricky. Like I said, hair doesn't fossilize. You can't dig up a 1.5 million year old human and check how hairy they were. But you can look for indirect evidence, clues in the archaeological record that suggest hairless skin had become important. One of the strongest pieces of evidence comes from the distribution of early human fossils. Around 1.8 million years ago, Homo erectus started spreading out of Africa into regions with very different climates. You find their fossils in Java, in China, in the Republic of Georgia. These are places with seasonal climates, places that could get cold. For a heavily furred ape, this expansion would have been relatively straightforward. You've got built-in insulation. But for a mostly hairless ape, you need something else. You need fire. You need shelter. You need the cognitive ability to plan ahead and create artificial protection against the elements. And sure enough, right around this time, we start seeing evidence of controlled fire use. Not just accidental fires that early humans scavenge from, but deliberately maintained fires in caves and campsites. The oldest widely accepted evidence of controlled fire comes from sites in Africa around 1 million years ago, with some controversial earlier dates pushing back to 1.5 million years. This timing isn't coincidental. The ability to control fire fundamentally changed what was possible for a hairless primate. Suddenly you could survive cold nights. You could expand into temperate regions. You could even use fire to process foods, making them easier to digest, which reduced the metabolic cost of digestion and freed up energy for that expensive brain you were growing. Fire and hairlessness went together. Not because fire caused hair loss, but because fire made hair loss survivable in environments where it would otherwise be lethal. Then there's evidence from stone tools. Around 1.7 million years ago, the stone tool industry underwent a major revolution. The simple Oldowan choppers that had dominated for hundreds of thousands of years were supplemented and eventually replaced by more sophisticated Acheulean hand axes. These were carefully crafted symmetrical tools that required significant cognitive planning. Some archaeologists argue that this technological leap reflects increased cognitive abilities associated with larger brains, which themselves were made possible by better thermoregulation through hair loss and increased sweating. It's all connected. Brain size, tool complexity, thermoregulation, hair loss. Each element supporting and enabling the others. But perhaps the most fascinating evidence comes from comparing modern humans with our extinct cousins, the Neanderthals and Denisovans. Through ancient DNA analysis, we can actually examine the genes of species that split from our lineage hundreds of thousands of years ago. And what we find is remarkable. Neanderthals and Denisovans share many of the same hair-related gene variants that modern humans have. The HR gene modifications, the FGF5 changes, the EDAR variants, they're present in all three species. This tells us that hair loss happened before the split between these lineages, probably at least 500,000 to 700,000 years ago, possibly much earlier. This makes evolutionary sense. Remember, all three species descended from the same bottleneck survivors around 800,000 years ago. Those survivors had already lost most of their body hair. They passed that trait to all their descendants, whether those descendants ended up in Africa, Europe, or Asia. What varied between the species wasn't whether they were hairless, but how they adapted to different climates after losing their hair. Neanderthals in Ice Age Europe didn't regrow thick body fur. Instead, they adapted through other means. Robust bodies with high metabolic rates, sophisticated use of fire and shelter, and eventually well-fitted clothing made possible by bone needles and advanced processing of animal hides. The ancient DNA from Neanderthals has actually revealed something else interesting about their relationship to hairlessness. Analysis of their genomes shows they had variants of genes related to skin pigmentation and UV radiation protection that were different from modern humans. This suggests they were adapting to lower UV environments in Europe, their lighter skin allowing more efficient vitamin D production in regions with less sunlight. This is crucial evidence for understanding one of the major advantages of hairless skin, vitamin D synthesis. Here's why this matters. Vitamin D is essential for calcium absorption, bone health, immune function, and a dozen other critical processes. Mammals produce vitamin D when UV radiation from sunlight hits a cholesterol compound in their skin. But if you're covered in thick fur, most of that UV gets blocked before it reaches your skin. You have to get your vitamin D from dietary sources, which is fine if you're eating a diet rich in fatty fish or other vitamin D containing foods. But if your diet varies, if you're expanding into new environments with different food sources, having the ability to produce your own vitamin D through sun exposure is a massive advantage. Hairless skin turned humans into vitamin D factories. As long as we got some sun exposure, we could maintain adequate vitamin D levels even if our diet was poor in vitamin D sources. This became critically important as humans expanded out of Africa into higher latitudes where UV radiation was less intense. Populations that moved north needed lighter skin to produce enough vitamin D with less sunlight, which is exactly what we see in the genetic record. Northern European populations evolved lighter skin relatively recently, probably within the last 40,000 years. Asian populations evolved different genetic solutions to the same problem, different combinations of genes producing lighter skin through different pathways. But here's the limitation we need to acknowledge. Ancient DNA analysis can only take us so far back. DNA degrades over time. The oldest hominin DNA successfully sequenced is only about 400,000 years old, from early Neanderthal ancestors found in a Spanish cave. We don't have DNA from Homo erectus, from Homo habilis, from any of the species that lived during the actual hair loss transition 1 to 2 million years ago. So everything we infer about the genetics of hair loss during that critical period has to be reconstructed indirectly by comparing modern humans with closely related primates and working backward. That said, the evidence is remarkably consistent. Genetics points to hair loss around 1 to 2 million years ago. Lice evolution confirms humans were hairless long before they started wearing clothes. Archaeological evidence shows the spread of fire use and sophisticated tools at exactly the right time, and comparative genomics with Neanderthals and Denisovans confirms that hairlessness was already established in our common ancestor over 500,000 years ago. Each piece of evidence supports the others, creating a coherent picture of when and how humans lost their fur. The final piece of the puzzle is understanding how hairlessness became viable in the first place. Because here's the thing, naked skin is vulnerable. It burns in the sun, it freezes in the cold, it gets scratched and damaged easily. For hair loss to be evolutionarily advantageous, There had to be cultural and technological buffers that made the transition survivable. Fire was one, shelter was another. But perhaps most important was the development of more sophisticated social behavior and knowledge sharing. A group of early humans teaching each other how to maintain fires, construct windbreaks, process animal hides. These cultural skills made biological hairlessness possible. This is what anthropologists call gene-culture coevolution. Changes in our biology created opportunities for new cultural behaviors, and new cultural behaviors allowed further biological changes. We didn't just evolve hairlessness through random genetic mutations. We evolved it through a complex feedback loop where genetic changes enabled new technologies, and new technologies removed selective pressures that would have made hairlessness fatal. The archaeological record shows this happening in real time. Bigger brains associated with better cognitive abilities enabling more sophisticated tools and fire use. And all of it happening right when genetic evidence suggests body hair was disappearing. So when you look at the totality of the evidence, genetic, archaeological, parasitological, the picture is clear. Somewhere between 1 and 2 million years ago, probably closer to 1.6 million, based on the convergence of multiple lines of evidence, human ancestors lost most of their body hair. This wasn't a sudden mutation. It was a gradual process driven by strong selective pressures, probably related to thermoregulation and the increasing metabolic demands of larger brains. The genetic changes that enable this are written in our genome, visible in the modified versions of HR, FGF5, EDAR, and other genes that control hair growth. And the consequences of this change shaped everything that came after, from our expansion across the globe to our need for clothing, to the evolution of different skin pigmentations in different environments. We are, quite literally, the naked ape, and the evidence for how and when we became naked is hiding in plain sight, written in our genes, in the parasites that plague us, and in the ashes of ancient fires lit by our hairless ancestors more than 1 million years ago. 'Cause here's the thing about hair loss. It didn't happen for just one reason. Evolution doesn't work that way. You don't wake up one morning and decide to lose your body hair because you've got a really good explanation. That's not how natural selection operates. Real evolutionary change, especially something as dramatic and universal as losing the fur that had protected primates for 65 million years, that requires multiple pressures all pushing in the same direction. Simultaneously, relentlessly, for hundreds of thousands of years. So when you hear someone say the Savannah Theory explains everything, or it was all about parasites, or sexual selection did it alone, be skeptical. Each of these theories captures something real, something important, but none of them, not a single one, is sufficient by itself to explain why humans became the naked ape. Let's think about this systematically. You're an early hominin, maybe 2 million years ago. You're starting to spend more time in open grasslands, becoming a better long-distance traveller. The Savannah Theory is right about this part. Those environments are hot, and heat management becomes crucial. Individuals who can shed heat more efficiently have an advantage. They can travel farther, hunt longer, avoid heat stroke during midday activity. But here's where it gets complicated. Losing hair helps with cooling, sure, but it also creates new problems. You're more vulnerable to sunburn, more exposed to biting insects, more susceptible to abrasion from vegetation. For hair loss to be advantageous, the cooling benefit has to outweigh all these new risks. That's a pretty specific set of conditions. Hot, open environments where the advantages of cooling exceed the disadvantages of exposure. That alone wouldn't drive complete hair loss across the entire body. So thermoregulation gets the process started. It creates a selective pressure favouring reduced body hair in certain populations living in certain environments. But it's not strong enough, not consistent enough to complete the transformation. Enter parasites. Now you're a hominin with somewhat reduced body hair because your ancestors spent generations in hot, open environments. You're already different from your hairier relatives, and suddenly you start noticing something. The individuals in your group who have even less body hair, they're healthier. They suffer less from tick-borne diseases, less from lice, less from the skin infections that plague your hairier cousins. The parasite protection hypothesis kicks in as a second selective pressure. It's not competing with thermoregulation, it's complementary. Both pressures are pushing in the same direction, toward less body hair, and they reinforce each other. Less hair means better cooling, which means you can be more active during hot periods, which means you encounter more parasites, which means there's even stronger selection for reduced hair. It's a feedback loop. But even these two pressures together aren't quite enough. Because evolution is constrained by reproduction, it doesn't matter how good you are at cooling yourself or avoiding parasites if you can't find a mate and pass on your genes. This is where sexual selection enters the picture. As body hair begins to reduce for practical survival reasons, something interesting starts happening in human social groups. Variations in hair retention become visible, noticeable, socially significant. Some individuals retain more hair on their heads, their faces, their pubic regions. Others have less. And humans, being the intensely social creatures we are, start making choices based on these variations. Sexual selection doesn't drive the initial hair loss, but once hair loss is underway for other reasons, sexual selection accelerates and directs the process. It explains why we retained hair in specific locations. Head hair for sun protection and display, facial hair for sexual signaling in males, pubic hair for scent dispersal and sexual maturity indicators. These patterns don't make sense from a pure thermoregulation standpoint. They only make sense when sexual selection is part of the equation. So now you've got three selective pressures, all operating simultaneously. Thermoregulation favouring less body, hair parasite avoidance favouring smoother skin, sexual selection favouring specific patterns of hair retention and loss. Together, these create what biologists call a selective sweep, a strong, consistent directional pressure that drives rapid evolutionary change. But the story gets even more interesting when you add in the aquatic ape hypothesis. Now, most scientists don't accept the strong version of this theory, the idea that humans spent millions of years as semi-aquatic creatures. The evidence just isn't there. But the weak version, the idea that some human populations spent significant time in wetland environments, exploiting aquatic resources, that's actually pretty plausible. And if that's true, it adds another selective pressure to the mix. Not strong enough to drive hair loss by itself, but strong enough to matter in populations already losing hair for other reasons. Reduced body hair improves swimming efficiency, makes it easier to thermoregulate when moving between water and land, reduces drag and improves hydrodynamics. So you could have populations in East Africa losing hair primarily because of thermoregulation and parasite pressure, while populations in coastal or wetland regions are losing hair for those same reasons, plus the additional advantage of improved aquatic efficiency. Different pressures, different intensities, but all pushing toward the same outcome. This is how real evolution works. Not one grand explanation, but multiple pressures operating at different intensities in different populations, all nudging the species in the same general direction. Over hundreds of thousands of years these pressures accumulate. Hair that was once thick becomes sparse. Sparse becomes vestigial. Vestigial becomes nearly absent. But here's where the story takes another turn. Because humans aren't just passive recipients of natural selection, we're cultural creatures. We make tools, we control fire, we create technologies that change our relationship with the environment. And these cultural innovations create new selective pressures that feed back into our biology. Think about clothing. The moment some early human figured out how to wrap animal skins around their body for warmth or protection, the selective pressure for body hair changed. Suddenly, retaining thick body hair isn't as advantageous as it used to be. The insulation benefit is replaced by cultural adaptation. This doesn't cause hair loss, but it removes one of the main evolutionary reasons to retain it. Same thing with fire. Once humans gained reliable control of fire, maybe 400,000 years ago, maybe earlier, they could create warm microclimates even in cold environments. They could keep themselves warm at night, could survive in regions their hairier ancestors couldn't. Body hair for insulation became less critical. The selective pressure to retain it weakened further, and this creates a feedback loop between culture and biology. Cultural innovations reduce the evolutionary pressure to retain body hair. That allows further hair loss, which makes humans even more dependent on cultural adaptations like clothing and fire, which further reduces the pressure to retain hair. Round and round, each change enabling the next. The archaeological record supports this cultural biological feedback loop. The earliest evidence of controlled fire use coincides roughly with the period when human body hair was probably in the process of disappearing. Stone tools that could be used for hide processing appear at similar times. These aren't coincidences. They're evidence that human evolution was becoming increasingly driven by cultural, rather than purely biological adaptations. But the really fascinating part is what hairlessness enabled once it became established. Because losing body hair wasn't just an adaptation to existing conditions, it opened up entirely new evolutionary possibilities. With smooth skin and efficient sweating, humans could sustain aerobic activity for hours. This made persistence hunting possible. The ability to literally run prey animals to exhaustion over the course of a day. Hairless skin also made humans much better at fine motor control of body temperature. You can modulate heat retention by adding or removing clothing, by seeking shade or sun, by wetting your skin for evaporative cooling. Furry animals can't do this nearly as effectively. This gave humans unprecedented flexibility to exploit diverse environments. Even more subtly, hairless skin improved social communication. With faces and bodies clearly visible, humans could develop sophisticated systems of non-verbal communication. Facial expressions became more visible and nuanced. Body language became more important. Blushing, a uniquely human trait, became possible only after facial hair was lost. These might seem like minor advantages, but in a highly social species, the ability to communicate subtle emotional states could be the difference between cooperation and conflict, between group success and failure. And here's something most people never think about. Hairlessness made humans better at thermoregulation not just in hot environments, but in cold ones too. That seems backwards, but it's true. With smooth skin, you can add precisely calibrated layers of clothing to match environmental conditions. A furry animal is stuck with whatever insulation its coat provides. Humans can adjust, fine-tuning their thermal protection to changing conditions throughout the day and across seasons. This adaptability explains how hairless humans managed to colonize literally every terrestrial environment on Earth. From equatorial rainforest to Arctic tundra, from scorching deserts to temperate islands. No other large mammal has a comparable range, and that's partly because no other large mammal has the thermoregulatory flexibility that comes from hairlessness, combined with cultural adaptations. But evolution didn't stop once humans became mostly hairless. It's still happening, right now, today. Look at human populations around the world and you'll see significant variation in hair retention. People of East Asian descent tend to have less body hair than people of European or Middle Eastern descent. Some populations have thicker, coarser hair. Others have finer, sparser coverage. These variations reflect ongoing evolution. Different populations experiencing different selective pressures over the past tens of thousands of years. Arctic populations had less selective pressure for complete hairlessness, because clothing technology was essential for survival anyway. Tropical populations might have experienced stronger continued selection for reduced hair because of parasites and heat stress. Even within populations, there's massive variation. Some people are naturally hairier than others. Some lose scalp hair earlier. Some retain thick body hair well into old age, while others never develop much. This variation is the raw material of evolution. Natural selection acts on it, favoring certain variants in certain environments, maintaining diversity in others. What this tells us is that human hairlessness isn't a finished product. It's an ongoing process. Evolution doesn't have an end goal, doesn't stop once some ideal state is reached. As long as environments change, as long as there's genetic variation, as long as some individuals reproduce more successfully than others, evolution continues. We're not the final form of humanity. We're just the current one, and that brings us to perhaps the most important insight from this holistic view. Human hairlessness isn't special because it happened. Lots of mammals have lost hair or fur in various lineages. Elephants, hippos, whales, naked mole rats. What's special is the specific combination of factors that drove it in humans, and the unique evolutionary path it enabled. We didn't just lose hair and that's it. We lost hair as part of a broader package of adaptations that made us who we are. Upright walking, which exposed us to more sun and made cooling critical. Increased brain size, which generated more metabolic heat. Enhanced sweating capability, which required hairless skin to work efficiently. Tool use and fire control, which reduced dependence on biological insulation. Complex social structures, which made visible communication more important. Hair loss was both a cause and consequence of these other changes. It was enabled by them, and it enabled them in turn. You can't separate hairlessness from the rest of the human evolutionary story. It's woven throughout, connected to everything else that makes us human. So when someone asks why humans lost their body hair, the honest answer is, for lots of reasons, acting together, over vast timescales, in complex and interacting ways. Thermoregulation, parasites, sexual selection, aquatic adaptations, cultural feedback loops, all of the above, none sufficient alone, but together creating an irresistible selective pressure toward the naked ape. And we're still learning. New genetic studies are revealing the specific mutations that reduced hair growth in human lineages. Archaeological findings are clarifying when and where hair loss occurred. Comparative studies with our closest relatives are showing exactly which genes differ between hairy chimps and hairless humans. Every few years, someone discovers something that adds another piece to the puzzle. The mystery isn't completely solved. We still don't know precise timelines, still argue about the relative importance of different selective pressures, still discover surprising connections we hadn't considered. But that's how science works, not by finding one perfect answer, but by gradually building a more complete, more nuanced understanding of complex phenomena. Human hairlessness is yielding its secrets slowly, But each discovery reveals not just why we lost our fur, but what it means to be human. So here we are, at the end of a journey that began 1 million years ago, when our ancestors first started losing their body hair. We've travelled through scorching savannas and followed the persistence hunt. We've explored parasites and predators, controversial aquatic theories, and the power of sexual selection. We've examined genetic mutations and archaeological evidence. And through it all, one thing becomes crystal clear. The loss of our body hair wasn't just a quirky evolutionary accident. It was the beginning of everything that makes us human. Think about what we've discovered. When our ancestors lost their fur, they didn't just become naked apes wandering the African plains. They became something entirely new, something unprecedented in the history of life on Earth. They became the only mammals that could run for hours under the midday sun, sweating away heat that would kill any other creature. They became social innovators who needed clothing, shelter, and fire to survive, forcing them to develop technologies earlier and more sophisticated than any other species. They became visual communicators whose bare skin could display emotions, health status, and social signals with unprecedented clarity. But here's what's really extraordinary. Each of these changes individually would have been evolutionary dead ends. Being hairless in most environments is a terrible survival strategy. You're vulnerable to cold, to sunburn, to injuries that fur would protect against. Being dependent on technology for basic survival is risky. What happens when you can't make fire or can't find materials for clothing? Yet somehow, our ancestors turned these vulnerabilities into strengths. They couldn't survive alone anymore, so they became the most cooperative species on the planet. They couldn't rely on natural insulation, so they became the most technologically innovative creatures ever to evolve. They couldn't hide their emotions through fur, so they developed the most sophisticated communication systems in the natural world. The loss of body hair created a cascade of consequences that reshaped everything about human evolution. It drove us to master fire, not just for cooking, but for warmth and protection. That mastery of fire let us expand into cold climates our hairy ancestors could never have colonized. It forced us to develop clothing, and clothing technology led to the development of cordage, weaving, and eventually textiles that became markers of status and culture. It made us visible to each other in ways no other species experiences. You can read emotions on a naked human face far more easily than on a fur-covered animal. That visibility drove the evolution of complex social hierarchies and communication. Most importantly, it made us interdependent. A hairless human alone in the wilderness is probably dead within days. But a group of hairless humans sharing knowledge about fire making, shelter construction, clothing creation, and resource management, they could colonize the entire planet. And they did. From Africa to Europe to Asia to the Americas to the remote islands of the Pacific, modern humans spread everywhere. Not despite losing their body hair, but in many ways because of it. Our vulnerability forced us to become smart, social, and adaptable. It made us human. When you look at human civilization today, you can still see the echoes of that ancient transformation. We're still the species that uses technology to compensate for our physical limitations. We're still dependent on complex social cooperation for survival. We're still communicating through visual signals, though now it's fashion and body language instead of just bare skin and blushing. Every time you put on clothes in the morning, you're engaging with the consequences of evolutionary changes that happened 1 million years ago. Every time you adjust the thermostat or turn on a fan, you're managing the heat regulation challenges that drove our ancestors to lose their fur in the first place. every time you read someone's expression or gesture. You're using communication abilities that evolved because hairlessness made us so visible to each other. Our naked skin tells a story. It tells us that evolution doesn't always work through gaining new abilities. Sometimes it works through loss, through stripping away protections and forcing adaptation through vulnerability. It tells us that humans didn't conquer the planet through being the strongest or fastest, or having the sharpest teeth and claws. We did it by becoming dependent on each other, by turning our weaknesses into reasons to cooperate, by building technologies and cultures that could protect what our bodies no longer could. Before we close, if you've enjoyed this journey through deep evolutionary history, I'd love if you could take a moment to hit that like button. It really helps the channel reach more people who appreciate these deep dives into our ancient past. And drop a comment letting me know where you're listening from. I'm always curious about where these stories travel, what parts of the world are falling asleep to tales of our hairless ancestors, and if you haven't already, consider subscribing. There are so many more stories to explore about how we became human. As you drift off to sleep tonight, remember this. You are the descendant of creatures who survived because they lost their protection, who thrived because they became vulnerable, who conquered the world because they needed each other to survive. Our naked skin isn't a weakness. It's the mark of the most successful survivors in the history of life on Earth. Sleep well wherever you are. And thank you for spending this time exploring the deep history written in our bare skin.